for this. On your exam, there's a question on there that has you do a little bit of Googling. Because I gave you this wonderful flow chart. Hopefully you get to use it a little bit. It's a great little flow chart that allows you to run data into a meat grinder and pop out sausage that is a p-value and a test statistic and a significance. Sorry, I didn't mean to use it. But it's essentially what you do is you take data and you turn it into a test statistic which then carries a p-value. That's the whole point. We've been doing it for 6 weeks now, 7 weeks now. What I want to make sure you guys understand is that in the real world of statistics, you saw on your last project, you can't always use what are called these parametric tests. Parametric tests mean that the data is shaped a certain way, behaves a certain way, or there is enough of it. If you can say yes, yes, yes to all of that, you can use those tests just fine. So what I did with my breaking data up here was I made some box plots and some histograms to take a look at the data sets. Now your TI sucks at doing this. You can make 3 histograms, you can make 3 box plots, but I like labeling them like this. So here are the cantilever breaks, mini V's, and full V's. Stopping distances on the horizontal or on the vertical axis out here starts at 5 instead of 0. I can live with that, I guess. So looking at that, what do you notice about the stopping distances of the 3 different kinds of breaks? Cantilevers, mini V's, full V's. Give me some descriptive conclusions based on those. Mini V and full V are very similar. Same conclusion I came to, Linda, thank you. Mini V and full V, very similar. This guy down here, what do you think about him? That's a quick stopping. So quick, in fact, that it's that is definitely an outlier, isn't it? If you look at how tight that box plot is, this has to be an outlier. Okay, so technically speaking, I can should I take that out or should I leave it in? What do you guys think? Leave it in. Austin says leave it in. Leave it in. Emily says leave it in. Totally fine. Let's leave it in then. What's nice about having Excel is if you want to, you can very easily pop a data point out. Like that's 10, right? With 9.9. So if you go in there and actually grab that, you can just hit delete, and it'll reset the graph. Looks like there's a second outlier too. Now, with that statement, I don't think they're all that outlierish. Okay, there obviously are 2, but there's only 2 out of less than 20. That doesn't sound like outliers anymore. That just sounds like high variability in a data set. So I'm with you guys in leaving them in. Please, Veronica.
What are the ramifications, though, of taking data in and out?
Love this. Answer this question. I love this question. What are the ramifications of pulling data out of a data set? What's one problem with that? Don't think statistics. Think financial. Maybe it's not connected. And you spent money to get that data point. In my case, I spent time. I had to corral max into collecting these data points. If I start throwing them away, I'm essentially wasting resources and data that I collected if I know they were collected properly, yes? So that's a ramification of taking one out. It's one ramification of taking one out. Secondly is, I'm calling it an outlier, but I don't know why it was an outlier. Is it just high variability, or did I actually break differently in those 1 or 2 cases? Possible. Can anybody see a problem with leaving it in? What might artificially happen? You might artificially bring your average down where it should be higher. That's why I also like looking at the medians, which aren't affected by outliers. Medians, they're not very impressive right here. They're about the same. And there are hypothesis tests that test medians. As a matter of fact, some of you might find them on that little fill in the blanks part of the exam where I have you go online and look for what are called non-parametric. So this looks like well-behaved data. We got a couple things that might be outliers, although since the data set is so small, I'm tempted to believe they're just extreme cases of high variability. What does the data look like over here? What do my data look like over there? 3 bell curves. If you could say, yes, your data is roughly bell-shaped, there aren't any extreme outliers. Those purple guys down there are your outliers. Those purple guys. If you could say, yes, they look like they're bell-shaped. Yes, looks like no outliers. That sounds like we were doing t-tests before. So now we're going to look at what happens when you got to do more than just 2 data sets at a time. And the answer is, it's called an ANOVA. So I'm going to click through to here now. This guy right here is the name of the test that is used. Now, we're not going to do this by hand at all. And it's funny because in every other statistics course I've ever either watched online or heard about, profs very often make students do other tests by hand, even though I make you do one or two at the beginning by hand, then we never use technology. Nobody ever makes students do these by hand. And you're about to see why. You're about to see why. Now, why is it called an ANOVA? It's called an analysis of variance. An analysis of variance. It's a acronym for that. Analysis of variance. What I think is wickedly clever about it was made up by a dude named Fisher, who, if you remember, is the same guy that gave us the concept of a p-value. This dude Fisher was pretty prolific back turn of the 1900s into the early 1900s. Did you say that again? No, that was Guinness, or that was Gossett. Gossett was the tea distribution. Gossett was the tea distribution. He's cool for his own reasons. But Fisher, and what's cool about it is if you look at your little template sheet, there are 4 distributions: the Z, the T, the chi-square, and the F. Ha-ha! And that's why. Because Fisher is named after Fisher, who gave us this analysis. Pretty slick, pretty slick, pretty slick. And this is what's so slick about it. He knew that there was going to be a problem with confidence if we start pairing off these averages 2 at a time. So he said, I got to think about how to do it all at once. And he says, okay, I know I got this chi-square idea. I wonder if I can use kind of that chi-square idea in a similar way. So what he did was, he went and calculated all of the sample averages for the different sample. I shouldn't say I did this, but this is what he proposed to do. Calculate the individual sample averages. For the cantilevers, they average a 23-foot stopping distance, mini V 16.4, full V 15.6. So, what Linda said was the mini and full V seem to be pretty close, and they do seem to be pretty close on average as well. Then he said that was the observed sample average. How about the expected sample average? I don't know. There's your 3 observed sample averages. He's going to assume they're all the same. Because if you're trying to decide if one set of breaks is better than the other, the null hypothesis has to assume the opposite of that. Just like it always does. You have this belief, you want to test that one set of breaks is better than the other, you start by assuming they're not and try to disprove that, just like everything else we've done in this class. If you're trying to show that Mars is wrong, start by assuming they're right, and then try to show a contradiction. Same as this. If you're trying to show that one of those sets of breaks is better, assume it's not, try to arrive at a contradiction. Same thing for the past 7 weeks. The variances. Now this, you might not remember this from 243, and we've mentioned it a couple times in here. Variance is the standard deviation squared. And there's a reason why we use that. We'll get to it in a second. And here are the sample variances for each of the data sets. Notice they're fairly close, fairly close. That's squared feet, which doesn't mean anything as far as breaking distance, but squared feet. And then there's an expected variance. Boom, boom, boom. That's what this test looks at, are those variances. And it tries to see, if I look at the variance in 2 different ways, that means I have 2 different numerical approximations for it. If they're roughly equal in both approximations, that means the average is also most likely equal. Now the mathematics we'll see here momentarily, but you have to remember, how do you calculate a standard deviation? What is a standard deviation? We talk about it all the time in here, right? Plus or minus. What is the standard deviation from 243?
How far away you are from the mean.
How far you are away from the mean. Well, if you have a measure that's measuring that, you kind of therefore also have an idea of the mean. If the averages, if the standard deviations are the same, that means the averages roughly have to be the same under a certain set of constraints. We'll come back to that. We'll come back to that. All right. So, here's the way Fisher did it first. He said, the first thing, don't worry about it, Emily. We don't calculate these by hand. I'm trying to explain what the machine is going to kick out for us. Please, no, it's by hand. What it does is, it first estimates the average of the variances. So you take those 3 sample variances and average them, and you get about 4 points. Don't write this stuff down. If you want this, I'll send you a spreadsheet. This is not worth writing down. No. From the actual data. If you took the standard deviation of that data and squared it, that's the variance. That's all. So you have 4.5 square feet, 1.2 square feet, 3.2 square feet. Add them up, average them, you get about 4.5 square feet. So that's one estimate of the variance. Then, and this is where I think it's really super clever. I think this is wickedly super clever. You take the averages. You take the averages and you look at what's called a grand mean. Grand mean would be just simply averaging all the averages together. Okay, don't memorize that. If you need it in another class, you'll see it. Then you look at the difference from the grand mean from the individual means. You get these guys right here. And then, does this start to look familiar? O minus E squared. That's a chi-squared calculation. Then you take this guy right here, and you, oh, you can't see that because it slid off. You take a weighted sample variance of those, and you end up with 16.8 feet. Now, once you solve this bad boy for sigma squared, you end up with 335. Now, if you remember from the previous one, the first estimate was 4.5. The second estimate was 335. Do they sound like they're the same? They sound like they're different. And the reason they sound like they're different is the two different pieces of the ANOVA look at the variance in two different ways. In one of the ways, it's mentioned up there. You look at the variance between the groups, and then you look at the variance inside the groups. If the averages are the same, those variances should also be the same. The problem, however, is when you look at these two numbers, they don't look the same. They look vastly different from each other. That's what ANOVA does. It compares this very rapidly and very quickly to see if they look like they're roughly the same. If they're roughly the same, those two numbers should be about the same, which means if you divide them, it should be pretty close to what?
1.
Should be pretty close to 1. The further away from 1 you get, the more likely they're different. Just like in a chi-square. The further away from 0 you get, the more vastly different. That's why with the M&Ms, we had a test statistic of 2, which is not very far from 0. I'm like, crap, it's 2. Usually it's like 500. But it was 2 in class last time. Huh, that means it agrees. That doesn't look like 1. 335 divided by 4 doesn't look like 1, does it? No, it doesn't look like 1. So what you do is, the test statistic is going to be called F, for Fisher. For Fisher. All you've got to know is, that number tells you how far away from 1 you get, and the further away from 1 you are, the more likely the averages are different. This is why I wanted you guys to throw your numbers into your TI, because your TI will give you that number right away. You don't have this access to this sheet because I built it. Grab your TIs, and let's knock out one last in-class quiz with this idea. All right.